All right, the third thing that has an influence on the relationship on the binding of hemoglobin to oxygen is a molecule called 2,3-DPG. It's also sometimes called 2,3-BPG, the exact same molecule being referred to. So either 2,3-diphosphoglycerate or 2,3-biphosphoglycerate. And this is basically produced by erythrocytes under the conditions of low oxygen, or anything that produces anemia, or even instances where we are at higher altitudes, which are synonymous with lower partial pressures of oxygen, okay? So anytime tissues are not getting adequate amounts of oxygen, the red blood cells are going to produce 2,3-DPG, okay? It's going to be inhibited by oxyhemoglobin. So in states when oxygen is bound to hemoglobin, if there's a lot of oxygen around, that will inhibit or block the production of 2,3-BPG. Now, 2,3-DPG is going to decrease the affinity of hemoglobin for oxygen. So how is that going to shift our curve, left or right? If it decreases the affinity for hemoglobin and enhances the unloading or offloading of oxygen, right, makes it easier, how would that shift our curve? Just based upon what we just described. To the right, excellent, yes, I'm seeing that in the chat here. That would definitely shift our curve to the right. So 2,3-BPG is another one of those factors that gives us a rightward shifting curve, which we can see here, right? Here is the curve of just hemoglobin. Here is what happens in the presence of 2,3-BPG. We shift our curve to the right, where there is a higher partial pressure required to fully saturate hemoglobin, but a lower partial pressure required to unsaturate hemoglobin, right, to take those oxygens off. Another thing that can influence the way that hemoglobin behaves, we mentioned this before, is carbon monoxide. And carbon monoxide is going to have a greater affinity for hemoglobin than oxygen does. It also binds irreversibly. So it's going to bind onto those hemoglobin, those heme spots on hemoglobin and not want to come off. And so they're going to just take up spots where oxygen would bind, and that can eventually become fatal, as we won't be able to mobilize oxygen efficiently to oxygenate tissues. Okay, so these are two other molecules or compounds that can influence the way that hemoglobin behaves, carbon monoxide being exogenously introduced, and then 2,3-BPG being produced by erythrocytes under states of anemia or low oxygen or lower partial pressures of oxygen, which is higher altitudes, okay? And again, just thinking about our law of mass action here, if we have lots of 2,3-BPG, which is our product, we're going to drive our reaction in the backward direction, okay? So instead of saying left and right, we can also think about the forward or backward direction, and that is towards the production of hemoglobin, and then that 2,3-BPG, which is hemoglobin not wanting to be attracted or bound to oxygen. Okay. What we'll speak about now is how carbon dioxide can be transported in the blood using carbonic anhydrase. I think we introduced this idea when we spoke about this in the vasculature. So carbon dioxide can be transported in the blood with the help of carbonic anhydrase. And so carbonic anhydrase is going to catalyze the reaction where carbon dioxide and water can be converted to carbonic acid, right? And then that can be dissociated into some other things that we will speak about. But it's basically transported in our systemic and pulmonary capillaries as well as in the veins. And then oxygen can influence the way that carbon dioxide is transported as well. So as we mentioned before, hemoglobin has this weird kind of third-party relationship with these two, where if there's lots of CO2 around, it doesn't like oxygen. If there's lots of oxygen around, it doesn't like CO2. So oxygen is going to influence the way that carbon dioxide can be transported because of that weird kind of third-party relationship. If we think about the mechanisms by which carbon dioxide can be transported in the blood, there are three mechanisms to do so. It can be dissolved in the blood to a lesser extent, and we talked about this, right? Oxygen having the ability to dissolve in the blood about 1.5% Carbon dioxide having a higher ability to do so, about 5.5% in systemic arteries and 5.8% in venous blood. But it's not enough to move around all of the CO2 that we need to move around. So there are some other mechanisms to help. The most important one is going to be dissolving as bicarbonate. So this is with the help of carbonic anhydrase. And again, we'll talk more about this mechanism, but this is how the majority of our CO2 is circulated in our system with the help of carbonic anhydrase and the production of bicarbonate. And then again, to a lesser extent, we can have, as we just saw, some amount of hemoglobin being bound, or some amounts of CO2 rather being bound to hemoglobin. Okay. And so here we can see, again, just reiterating that relationship that CO2 can dissolve in our blood, in our plasma more easily than oxygen, and just pointing out the difference between the percent with which oxygen can dissolve, which was 1.5%, if you remember from the beginning of our previous packet, and then comparing that to 5.5 to 5.8% for carbon dioxide. So just kind of reiterating that idea that CO2 dissolves more easily in the blood than oxygen, but even saying that dissolving is not the only mechanism for moving CO2 around in our system. Okay. So here is that mechanism, that reaction. So carbonic anhydrase can catalyze water and CO2 being produced into carbonic acid. And carbonic acid is then going to dissociate into bicarbonate and hydrogen ions, and those things can move around in our system. They also play a very important role in our acid-base balance because bicarbonate is alkaline, hydrogen ions are acidic. This is going to also help us balance our acid and base, right? Acidity and alkalinity in the blood as well. And we'll talk about this at the end of this unit, as well as in the lungs, so not the lungs, but the kidneys. The kidneys also play a role in that acid-base balance. Okay, here we're just looking at how CO2 transportation in the blood can be affected by oxygen. And we kind of made that point a little bit earlier. Oxygen does have an effect on the way that we can move CO2 around in our blood. And so here we're thinking about the total amount of CO2 being transported and comparing that to the partial pressure of CO2, as well as different partial pressures of oxygen. In other words, different amounts of oxygen in our system, in our arteries. And what we're saying is that at lower partial pressures of oxygen, there's more CO2 being mobilized in our blood. At higher partial pressures of oxygen, there's less CO2 being mobilized in our blood. And that is for a given or set or fixed partial pressure of CO2. Okay, so the higher partial pressure of oxygen, meaning the more oxygen that's circulating in our vasculature, the less CO2 that is mobilized. And again, this is that third-party relationship with hemoglobin. If there's a lot of oxygen around, hemoglobin does not like CO2. If there's a little bit of oxygen around, hemoglobin does not like, if there's a little bit of oxygen around, hemoglobin does like CO2, okay? But even saying that, this transport of CO2 in the blood is not just the carbon dioxide that is bound to hemoglobin, it's all the carbon dioxide. So all three of those mechanisms, whenever there's more oxygen around, all three of those mechanisms decrease. Whenever there's less oxygen around, all three of those mechanisms will increase, all right? Okay. Okay, so I'm gonna explain that again. So someone's asking me to just kind of go over that one more time. So we're thinking about a given or standard amount of CO2 partial pressure. And the reason that we're thinking about this as being fixed is that if there's a fixed partial pressure of CO2, we wouldn't ultimately expect there to be a difference in the amount of CO2 that's being mobilized. But there is, under the influence of oxygen. So whenever there's more oxygen around, there is less of an ability to mobilize CO2 through all three of the mechanisms that we talked about, dissociated into bicarbonate, dissolved in the blood, as well as bound to hemoglobin. If there's more oxygen present in our system, all three of those mechanisms become less efficient and less CO2 in general, in total, is circulating in our blood. At higher partial pressures of oxygen, meaning more oxygen, at lower partial pressures of oxygen, meaning less oxygen is around, then we see more of that CO2 being circulated in our system, right? And again, through all three of those mechanisms. So more of it can be dissolved into our blood, more of it can dissociate into bicarbonate, and more of it can bind onto hemoglobin. And that is just showing us that oxygen influences the way that CO2 is mobilized through all three of those routes in our circulatory system. Okay, I hope that added some more clarity there. Okay, this is just a flow chart that describes the way that hemoglobin behaves differently under the influence of partial pressure changes of oxygen and of hemoglobin. So in this first flow chart, we're looking at what's happening to hemoglobin if there is a lower partial pressure of oxygen, and we know by Henry's law that is synonymous to meaning that there's less oxygen around. And if there's higher partial pressure of CO2, which again is synonymous to meaning that there's more CO2 around. So if we think about the drop in partial pressure of oxygen, that will directly create an ease of unloading of oxygen from hemoglobin. So less oxygen is going to mean that hemoglobin is going to dissociate more easily, or oxygen, is going to dissociate more easily from hemoglobin, and is going to increase the ability of oxygen to unload into our tissues. And if we think about those instances of increased metabolic activity, that's why I keep bringing that up, because it's a holistic way to think about this and kind of walk yourself through why we see an increase in unloading. So if my tissues are exhibiting an increased metabolic demand, there's less oxygen around because they're consuming more of that oxygen. And so I'm shifting my curve to the right. And so oxygen will dissociate or unbind or unload from hemoglobin more easily. If we think about CO2 and how CO2 plays a role in that, decreased levels of oxygen are synonymous with increased levels of CO2. And CO2 is going to have a direct effect on the amount of CO2 that can load. If there's more CO2 around, more of it is going to load. And according to the Carbamino effect, more CO2 is shifting our curve to the right, meaning that there's a decreased affinity of hemoglobin for oxygen, which is also saying that oxygen will unload or unbind more easily from that hemoglobin. And then the other way that CO2 does this is CO2, if we go back here, CO2 can be converted into carbonic acid, which, as I mentioned, can then dissociate into bicarbonate ions as well as hydrogen ions, okay? And those hydrogen ions, jumping back here, also exhibit the Bohr effect. If there's more hydrogen ions around, there's more acidity around, that is also going to shift our curve to the right and influence the way that hemoglobin behaves, in that it's going to decrease the affinity or attraction of hemoglobin for oxygen and make it more easy for that oxygen to unload into our tissues, okay? So having low oxygen, high CO2 through direct and indirect mechanisms just changes the way that hemoglobin wants to bind to oxygen. It does not want to attract to oxygen. It wants to easily offload that oxygen into our tissues to combat the instances of low oxygen and high CO2. Okay. And then thinking about the reverse. So here's another flow chart thinking about the opposite scenario. If we have lots of oxygen around and a little bit of CO2 around, we're going to see the opposite sequence of events. Through direct mechanisms, we're going to see more oxygen being loaded onto that hemoglobin, right? Although it's not saying it here, when we say loading, we mean loading oxygen onto hemoglobin or binding it onto hemoglobin. Whereas when we're saying unloading, we mean binding it off, removing it, and sending it out into the tissues. So more oxygen means that more of it is going to bind onto hemoglobin directly, but then more oxygen is also synonymous with less CO2. And less CO2 is going to directly increase the unloading of CO2, meaning CO2 is being removed from that hemoglobin. Again, think about that third-party relationship. Lots of oxygen around, all of a sudden, hemoglobin doesn't like CO2. Okay, so it's gonna appreciate or prefer whatever is around. And then also thinking about the ability of CO2 to dissociate into hydrogen ions. If there's less CO2 around, that means there's less hydrogen ions around. In other words, more acidity around. And so that is going to, less acidity around. So less hydrogen ions, less acidity around. And so that is going to also lead us to thinking about the Bohr effect, right? The Bohr effect says that if there's less hydrogen ions around, less acidity around, then there is going to be less of an attraction. Well, hang on here, I'm kind of mixing myself up. So we have less hydrogen ions around, which is actually more acidity. We're going to see more of an attraction of oxygen for hemoglobin, so that tight binding of hemoglobin, and it's going to have more of that effect to load more oxygen onto that hemoglobin, okay? So we're thinking about the amount of oxygen or CO2 that's present and how that influences whether or not hemoglobin wants to bind to oxygen if lots of it is around, or to CO2 if lots of it is around, and then how that affects it loading versus unloading, and loading being binding of that oxygen onto hemoglobin, whereas unloading means removal of that oxygen and sending it out into the tissues. Okay. All right. I'll pause here and see what questions we have, and then we'll take it from there. All right, so let's look at a few practice questions. Okay, hang on here, a few questions coming up. So someone's asking to clarify if less hydrogen ions means less acid. So less hydrogen ions means less acid and more alkalinity, all right? More hydrogen ions means more acid. Okay, I kind of messed that up there. But less hydrogen ions, less acidic, more alkaline. More hydrogen ions is more acidic and less alkaline. Okay. All right. Any other questions? Any other questions on that bit? Okay, let's look at this practice question. All right, final couple seconds. Okay. So a lot of response for B. How do you think the hemoglobin oxygen dissociation curve would shift if we went from New Orleans, 7 feet below sea level, to the top of Mount Evans, which is 14,265 feet above sea level? And so many of you selected B, which is a right shift, and that is correct, okay? But make sure that we understand, quite a few of you selected A as well, the reason that it is not a left shift. It is a right shift because, that's okay, someone said they meant to put B. So it is a right shift because we're thinking about higher altitudes, lower partial pressures of oxygen, and then these are scenarios that make it easier for oxygen to unload or offload into those tissues, okay? And as we can see here, anything that does that shifts our curve to the right. And it's not a left shift because a left shift would be if we went below sea level. So if you went below sea level where you had higher partial pressures, oxygen and hemoglobin would have a tighter attraction, a tighter affiliation, and it would be harder to unload or to remove that oxygen from hemoglobin. Okay, and again, thinking about all of the things that we said that shift this curve to the right, high metabolic activity, synonymous with more CO2, okay, more acid production, which is a lower pH. I think that's what I meant to say. So more acid is a lower pH, but it is also more hydrogen ions, okay? So more hydrogen ions, more acid, but lower pH. And so all of those things are going to be synonymous, exercise included, with shifting our curve to the right, making it easier to get that oxygen off of hemoglobin and mobilize it out into the tissues.